Greetings to all. Today we are presenting our paper on low light scene enhancement for object detection and tracking using multiscale decomposition and fusion. One of the first but indispensable tasks in computer vision is object detection. When there is insufficient light available, the performance of object detection is significantly impacted. Moving object detection and tracking is crucial task in many video-based applications like surveillance, event monitoring, weapon system tracking, etc. Here we are proposing a method that employs image fusion rules for improved object detection to overcome the drawbacks of low-light video monitoring. Low-light object detection and tracking is challenging since current approaches have drawbacks like overexposure, noisy output, or even insufficient illumination for effective object detection. The benefits of the state-of-art techniques are combined with new features to improve segmentation, which makes object detection easier. A crucial problem in computer vision is tracking many objects in video. It is utilized in a variety of video analysis situations. Bounding boxes are installed around each object in the image in order to track it using precise location of the object to be detected. Thus, object detection is utilized for this. So, for locating and detecting, segmentation is essential and crucial to object tracking. Low light conditions result in less effective segmentation of video surveillance as the object cannot be contrasted to the background. Therefore, low light images should be enhanced. Here we discuss the algorithms used in proposed methodology. NSCT. In order to stop the sampling process that takes place during image decomposition and image reconstruction, NSCT is applied. It divides the images into contour segment-like pieces. Compared to the current wavelet approaches, it is more effective at capturing the geometrical structure of an image. D-shift. By describing the local gradient information for a discovered interest point, its shift descriptor is created. As a result, it is possible to create activity level assessment for images using the underlying salient information contained in the shift descriptor. Nevertheless, the shift descriptor cannot be used directly in the field of pixel level image fusion since the activity level measurement must be assigned to each pixel or at the very least each block. Dense shift eliminates the need for interest point detection by extracting a feature descriptor for each pixel in an image. Contrary to shift descriptor, dense shift descriptor is neither scale nor rotation invariant, but fortunately, because the dense shift descriptor of a pixel is obtained by utilizing the gradient information of every pixel in its local patch, the associated activity level measurement is more accurate and noise resistant, which can be used for fusion. MSR. In contrast to Retinex theory's original goal of describing human color perception, its derivations have produced effective algorithms for boosting local image contrast. The most effective center surround image filter from these derived algorithms is multiscale Retinex. Single-scale Retinex SSR demonstrate that it can only accomplish either dynamic range reduction or color rendition at once. MSR for the majority scenarios gets around this restriction. The output of the MSR is weighted sum of the outputs of many SSRs. At the transition between the bright and dark areas, the MSR-based images exhibit significant dynamic range compression and overall image scale exhibits acceptable color rendition. So we use it to create weight maps for exposure and contrast in our method. Maximum selection rule selects the maximum pixel value between the input images. CEGEF. The edge and texture information from high-frequency image clusters are preserved thanks to the proposed clustered edge gradient enhanced fusion rule. The high-frequency images are employed to capture the fine features in image. Hence, we propose this rule to capture an upgraded version of the image. It uses FCM technique to enhance the correct information included in high-frequency coefficients and eliminate information such as defective edges or noisy features resulting from low exposure. And then it employs a gradient-based edge boosting rule to create the final high-frequency image. This is the flowchart of the processes for the proposed enhancement technique. In order to separate the image into low frequency and high frequency, we employ NSCT. in contrast to the edge features in the high frequency image, which are enhanced using clustering and noble gradient based filter. The low frequency image is subjected to two enhancement filters independently as illustrated, then combined with maximum information integration. Then inverse NSCT is finally applied. Here the sources of our data sets are shown. For our experimentation we have used MATLAB, and we manually segmented and labeled the ground truth images as shown. We later compared all the data using edge cutting techniques, which also included tracking results after enhancement. To demonstrate how our proposed way of improving low light images aids in better segmentation and subsequently tracking, we employed a similar tracking algorithm across all the methods, that is ORS tracking rule. The original images and the comparison approach are shown in figure 1. This footage was captured from a low light surveillance system. As compared to other methods that are provided, it is clear that our proposed method has successfully maintained a balance between contrast and exposure along with the denoising of image frames. In the second section of figure 1, we can demonstrate how our technique can function just as well in colored frames without adding any extra artifacts or color distortion. These are several image sets which come from XDark dataset, allow us to better understand how our proposed methodology preserves the finer features while enhancing image satiation and exposure without adding any extra noise effects. This slide, figure 3, displays the outcomes of the improvement process. We can observe how our suggested enhancement strategy works by precisely segmenting the moving object in the frame and removing other unnecessary information, which obviously makes it easier to precisely track the specific object represented using the bounding box. Here are some additional tracking results. Here we give the objective measures that allow us to quantitatively compare our method to other methods and realize specific aspects of it. The proposed strategy is superior for the majority of the measures on average, but from an unbiased standpoint, we can observe that some metrics are slightly better in other methods. If we look at the precise image from a subjective perspective, we will see that it hasn't been fully enhanced or has effects like blur and noise, which shows that the enhancement procedure for other ways isn't quite sufficient. Additionally, as these are the average values for the objective matrix for each image frame, we cannot argue that they are sufficient on their own for all images. Overall, compared to other methods, our proposed approach has improved detection and is more accurate to the ground truth images. The results demonstrate that the proposed method of image enhancement, which improves the low light image both visually and quantitatively, performs better in moving object segmentation in low light condition. It is evident from the subjective analysis point of view that proposed approach improves and sharpens low light image frames, also minimizes noisy effect. On the other hand, it is observed in other methods some augmentation is present, but introduction of noise and blurry effects arises when enhancing the image. It is evident from looking at the segmented images that the suggested method allows improved detection and is more comparable to the ground truth image. The majority of the metrics are on average better for the proposed technique. This research demonstrates an enhanced fusion enhancement technique to address the issue with the low light video images. We presented a better fusion through a novel filtering approach in order to address the challenging noise issue and contrast issue in low light video images. The multi-target tracking is observed in our methodology shows better result than other method as provided. In future, we will gather more data from the field and try to implement the proposed methodology to see how it performs as well as improve it to allow faster computation so that it can be applied to real-time video. These are the references used. Thank you.